Hello everybody, my name is Noah Ransom and I'm joined with my good partner Caleb Bosey. Today we will be talking about our digital sound processing project and some of the struggles and successes we had along the way. On the agenda today we have an introduction to the team, defining the problem that we are trying to solve, understanding available solutions out there on the market, project achievements and milestones, competition and market analysis and overview, the technical description of what is DSP, what is Sigma Studio. We have also a budget, challenges we faced, the complexity of DSP, learning new software, time management, writing the report, working remotely, and the lessons learned, and our conclusions. To introduce myself, my name is Noah. As mentioned earlier, I have a diploma in audio engineering, and I am also working on an album.
Hi, I'm Caleb Bose. I have a background composing music for various indie video game projects and have played in several bands. So why do we need room correction? Well, because sound is a wave that travels outwards, or propagates, into the space available, and unfortunately, flat walls, as we often prefer in our homes, don't do a particularly good job at stopping reflections. So, in this first image, I have the audio source, the television, highlighted in yellow. The sound from the speakers propagates outwards into the space of the room, and you hear the sound. This is how we want it to function, and that's wonderful. However, let me give you an image that's maybe closer to the truth. In this rather psychedelic image, I'm showing reflections from a few of the other surfaces in the room, and things get pretty messy. I'm not even including all of the surfaces for clarity's sake, so it's probably even messier. The big problems in the tuning of a room occur where these areas overlap. Sound waves are just compressions or expansions of air, so when two expansions meet, they might add to each other or compound, and when a compression and expansion meet, they might cancel each other out. This can lead to strong imbalances in certain frequency ranges or areas in the room, which is what room correction and a large part of the DSP Box product aims to fix. For example, the brown chair in the room might be the place where you listen to the majority of your music or television. And unfortunately, as you can see from the second image, this area has a lot of overlap, which might result in improper sound at that location. So you would use room correction to tune the room so that that location hears audio the clearest or the best.
Currently, there are three categories of solutions for this type of room correction. There's old analog equipment that you can buy used, which is unreliable, noisy, and cheap, which is a good thing for the last one, but the rest is very, very bad. There's also new analog, which is amazing quality, but extremely expensive and doesn't really offer a whole lot of user feedback on if they're doing good things or not. Lastly, there's digital processing. There is far more control and far more potential there with digital processing than any type of analog equipment. It also offers the cleanest sound, which will be most accurate to the recordings that you're trying to listen to. It is also between the middling and high end of cost, so there is some room to be made there. Of those three solutions, there are two particular products that stand out. The Mini DSP 2X4 HD for about 290 Canadian dollars offers far more functions and in-depth signal chains than what we have, but is far beyond what the average person can get behind or really needs. There's also the Shit Loki for 200 Canadian dollars, which is extremely limited due to its analog nature and requires a lot more components to function to its fullest potential. Currently, our DSP box sits in at about 55 Canadian dollars for the Raspberry Pi and 120 Canadian dollars for the DAC chip to go along with it. We would also need to factor in the cost of 3D printing an enclosure. So how is DSP Box different? There are two main categories that we are trying to push the envelope for: seamless integration and upgrade paths. We are an all-in-one solution, which means that there's less clutter in your listening area. So every possible function that you could ask for a box to have, we have it in one. We also have future upgrade paths. So if there's one particular component that you do not like about the DSP box, you can upgrade it and still use all the functionality of that solution. Our project achievements and milestones are as follows. In 2019, the project began as a discussion between myself and Andrew Huddleston about the potential of audio and how we can sort of incorporate our passion for audio into a final project. By the end of that discussion, we had decided on a few different ideas, and we eventually settled on DSP as being the one with the most potential. In October, Caleb joined me, and we began research into hardware and software options for the project. In November, we initially used the Arduino for prototyping, but quickly discovered that the Raspberry Pi was far superior in every way. In December, our report shell had been constructed, and we found out about the Hi-Fi Berry team and their DAC plus DSP chip, and that motivated us to stick with the Raspberry Pi as the base for our final product. As 2020 came through, our research continued into DSP thanks to the book The Scientist and Engineer's Guide to DSP, which is free on the internet. In February, we received the hardware and assembled it and began developing the Sigma Studio signal chain for our device. March came through and our first revision of the signal chain had been created and the GUI process could begin. Unfortunately, this is when the worldwide health crisis began and continued development became more challenging.
What is DSP? Digital signal processing is an area of computer science that deals with a complex type of data, signals. DSP is the process of converting these analog, real-world signals into binary computer data and then performing various mathematical operations on them in order to produce a desired result before then converting back into an analog signal. For our specific application, we take an audio signal, usually the result of the output of some sort of multimedia device, and pass it through an analog to digital converter. Break the audio signal down into its constituent sine waves with Fourier analysis, perform the operations required to do equalization, filtering, or effects to these specific sine waves, and then recomposite the sine waves back into an analog signal using a digital to analog converter.
All right, so this is our lovely Sigma Studio software here. This is where our main signal chain for our project comes through. This is where all the magic happens. So starting off, we start down here. This is our input from the Raspberry Pi, pin 16 and 17. This comes into our input selector, which if we open up on this page here, we have three different inputs. We have the Raspberry Pi audio, which is native, goes right through. We have the SPDIF input, which is a optical audio input. This one's lowered because that optical audio can be pushed really high in terms of volume. So we lower that coming in automatically. And we also have an analog input here, RCA, that's for different add-on boards for our product if it ever goes live. Next up in the main, we come through the input selector, which we just went over, and we go into the volume here. This lowers absolutely everything by, again, about 18 decibels. This is just to make sure that nothing is clipping whatsoever. Just to double check that everything's not clipping, we have a limiter right after that. At this point, if anything's clipping, it'll be reduced in volume, and this will affect the overall sound output. But if we didn't reduce sound at this point, it would break equipment, and we want to make sure that nothing that ever happens. Coming up here, we have the balance. This is our left channel and right channel in stereo, how much one side gets volume versus the other. We have these in decibel formats right here, and just simple as lowering and raising. Next up, we have our channel select, which is right here. This is just a future module. We were experimenting with 7.1 and 5.1 surround sounds. This is outside the scope of our project, but we are tinkering with it anyways. Next up is equalization right here. This is our bread and butter when it comes to this sort of room correction. So we have a generic 2x16 equalization. So we have the right channel here, left channel here, and that goes through a second tone control here. We did tinker with a separate chunk of software called BeoCreate for external commands. This was just an automated version of EQing, but we wanted to have people have manual control on top of the automated control. This one didn't really quite make the cut, but it still passes through everything. Next up, we have filtering, which is right here. You'll notice that it looks a lot like EQ, except just stacked on top, just so many stacks. We have left and right channel here, and it just goes through into the outputs here. After that, we have a growable delay. So depending on the amount of load on the DSP chip based off of sudden parameter changes, the DSP might need a small amount of delay just to catch up with everything. And these delays allow us to do that and make sure that everything is safe. Coming out here, if you don't want to use the normal RCA outputs, the analog outputs, and want to go strictly digital, there is a SPDIF output on the chip. So that comes down to the SPDIF output here, which we have a toggle. Thanks so much. We'll see you around. All right. Our budget breaks down as follows. About $55 for the Raspberry Pi, 120 Canadian dollars for the DAC plus DSP chip, $30 in shipping and handling fees, bringing the total to about 205 Canadian dollars. Thanks to most of the software for this project being open source, we are able to keep the cost of this project quite low.
The challenges we faced. The complexity of DSP. Digital signal processing, as it turns out, is not a simple topic. When we had decided upon the project, we had a somewhat vague understanding of the levels of maths and computer science required to achieve it. This became more and more apparent as we moved forward. For example, we were taking calculus and about to learn Fourier series when we realized that that would be integral to our understanding of how DSP works. Learning new software. Developing the project took us well outside the scope of our engineering technology skills. We were forced to learn several new technologies, including the Sigma Studio development workflow, new Python libraries, and Fusion 360. For example, with only a basic programming course under our belt, it became increasingly difficult to adapt to the new libraries we were forced to work with. Time management. As a team with only 2 members, managing time for such a large project taking place in parallel with so many other demanding courses was a challenge. Writing the report. Learning to assemble a technical report on a project before it's completed was also a new experience for both of the team members. It was difficult to juggle the process of developing the technology with where the report was supposed to be, as the report was being developed in parallel with the actual development of the project and being written from a perspective of the project already being done, which was incredibly challenging. Working remotely. Developing the technology separately, especially with only the one prototype, made a lot of decisions and development slower and more difficult than anticipated. Correspondence back and forth between team members was not always instant, as we coordinated mostly online. Lessons learned. What did we learn? Well, we've gained a wealth of understanding in the field of DSP, which has applications in many different fields and is of incredible value. We learn new software such as Fusion 360 and Sigma Studio and gain experience with various new libraries in Python. Pygame, for example, for GUI development. We learned how to document the entire process and how to structure such a large document as to make writing simpler and more efficient. What would we do differently? Next time, we would try and perform more preliminary research and make sure that the project complexity isn't so much higher than we initially anticipate. We would also focus on a more tangible project with wider mainstream applications, such as something focused more on hardware and less on software, as the average person does not necessarily see the value of DSP as of yet. What is the biggest takeaway? The biggest takeaway is probably how important it is to be flexible, especially early on in the life cycle of a project. Understanding when red flags appear and being able to pivot is necessary to ensure success. To avoid the sunk cost fallacy, and for example, if we do end up finding ourselves in a hole, to stop digging as early as possible.
Thanks for listening to our presentation. If you have any questions, feel free to email us in the slide that we introduced ourselves in, and we'll be happy to get back to you. Special thanks to Professor Huddleston for the idea, Mauricio for the technical support, and Professor Carolyn Cote and Leanne Nicholson for the English support. Thanks so much for listening. I hope you guys have a great day.